I'm about to try to diagonalize this matrix, but in doing so, we're going to run into difficulty. It's not diagonalizable, though it's not obvious why. It doesn't look like it's necessarily not diagonalizable. What's the characteristic polynomial? Lambda squared minus t lambda plus d will be lambda squared plus 8 lambda plus the determinant will be 15 plus 1 is 16. What are the eigenvalues? This factors is lambda plus 4 times itself. Lambda plus 4 squared is how this factors. It's got a repeated eigenvalue. The only eigenvalue is -4. It's got algebraic multiplicity 2. Algebraic multiplicity 2, meaning that in the factorization of the characteristic polynomial, that's the power there. Just because it's got algebraic multiplicity 2 does not necessarily imply that the matrix is not diagonalizable, though it makes it likely not diagonalizable. There are examples where the multiplicity is 2, but it is diagonalizable. In particular, any scalar multiple of the identity matrix has a repeated eigenvalue, but it's already a diagonal matrix. What happens if we try to find eigenvectors? Lambda equals -4. The system -5 minus -4 is going to be -1 times x plus y equals 0. And with the second equation, just to confirm, we get -x, -3 plus 4 is +1. We get the exact same equation. So y is x. And so your eigenvector is 1, 1. And there are no other eigenvectors that are not scalar multiples of this. All eigenvectors are going to be scalar multiples of this, non-zero scalar multiples. One line of eigenvalues, as you would typically expect, the eigenspace is one-dimensional. And that's the only eigenvalue. So how are we going to come up with a matrix P? And with the Book's method, how are we going to come up with two linearly independent solutions that a linear combination of those would be a general solution? It's not clear what to do. The Book's method is fine and probably simpler than the Jordan canonical form approach, but I do want to teach you about the Jordan canonical form approach, even though it's complicated. It's worth knowing about. The 2x2 case is definitely the easiest case. You go to 3x3 or bigger, it's definitely a lot harder to do the Jordan canonical form. We're wondering, I mean, it's still not clear that we can't diagonalize this. I'm claiming we can't, but that's not clear. We're wondering, maybe I start to make a matrix P, and I go ahead and make this the first column, and maybe there will be some other column that I can put here and here that will still diagonalize it. You know, we're kind of hopeful. Maybe something like this will work. It won't, but we're going to try. It's worth trying. But it's unknown what B and D should be. So I'm going to try to solve for B and D here to maybe make this diagonalizable, even though I will fail. It'll still be worth doing. Okay. So the determinant's going to be D minus B. I'm writing down P inverse here. So I do 1 over D minus B, switch the entries on the main diagonal, negate the ones on the off diagonal. P inverse, as long as B does not equal D, does exist. I guess I'm rewriting the exact same thing. I didn't need to do that, huh? Pretend I didn't do that. I'm wondering if what's going to happen now if I compute P inverse times A times B. I think initially I was imagining I'd multiply this through, but I think I'm going to leave the fraction out in front. What happens if I do this multiplication? Anything worthwhile happen for certain choices of B and D? Okay, let's do it. Multiply these two. It's not going to be super pleasant, but hang with me here. -5 plus 1 is -4. -5b minus 3d. -1 plus -1 plus -3 is -4 again. -b minus 3d. Double check that. Keep going. Something nice does happen if you don't make a mistake here. Let's see. -4d minus 4b, or plus 4b, excuse me. I can factor a -4 out of that and write it as -4 times d minus b. That's nice. Question? -5b plus d. Yes, I don't know. I was looking down there, I guess. This should be a plus d. Thanks. But here, this is correct. -4d plus 4b is the same as -4 times d minus b. Yeah, the d minus b's will cancel as long as d doesn't equal b. And upper right, -5bd plus d squared plus b squared plus 3bd. Even though that's not so pleasant, it does turn out to simplify nicely. Lower left is really nice. -1 times -4 is +4 times, or plus -4 is 0. So this not being 0 necessarily means this is not going to be diagonal, but it is going to be upper triangular. And then the last one, lower right, is going to be 5b minus d minus b minus 3d. And that's the same as -4d plus 4b is -4 times d minus b. Yeah, if d does not equal b, those cancel. Assume d does not equal b. And what about this? This simplifies to d squared minus 2bd plus b squared, which can be factored as d minus b quantity squared. Amazingly. And one of those terms will cancel too. So as long as d does not equal b, this simplifies to -4, 0, d minus b up here, and -4 down there. Not a diagonal matrix, but upper triangular, you might say, the next best thing. And with this Jordan canonical form idea, you're not just after any old upper triangular matrix. You want that entry to be 1. Why? Because it's just the simplest thing to pick. You actually could pick it to be something not equal to 1, but that's not the method. That's not the algorithm. Want this to equal 1 for Jordan is spelled like Jordan. Jordan canonical form. Again, for emphasis, not that it couldn't be something else. It could be, and it would be okay, and you could still solve the system. But just sort of as a standard method to pick the simplest thing that's non-zero, we pick 1. So choose b and d to be so that d minus b is 1. Can that be done? Sure. I could choose any numbers here for B and D so that D minus B is 1. I might as well pick B as 0 and D as 1. So now it's effectively, I'm going back up here and I'm picking D to be 0 and D to be 1. So my P matrix now is something specific, 1, 1, 0, 1. With inverse, 1 over 1, positive 1 there. Inverse equal to this. And again, D is not diagonal. Maybe I shouldn't call this D because it's not diagonal, capital D. But it is special. It's upper triangular. You could call it U for upper triangular. Or we could call it J in honor of Jordan. But we're going to use this P and this P inverse. Not a unique P and P inverse. I could have picked a 1 and a 2 there. Or a 2 and a 3. Or a 3 and a 4. As long as D minus B is 1, that'll work. But 0 and 1 are the simplest to pick. So you'd use this P and this P inverse and this J, and you're going to end up solving the system in the end using matrix exponential. In the same way as before, the only difference is now instead of e to the TD, you got e to the TJ. But this is still easier to compute than e to the TA directly. Still relatively easy to compute. We're about out of time. The details are in the lecture. You can look at the PowerPoint. You can watch the lecture, or part of the lecture at least, where I finish this. I will say you've got to pay attention to details regarding something called a nilpotent matrix. What's a nilpotent matrix? Well, any matrix whose square is the 0 matrix is an example of a nilpotent matrix, like this matrix here. If you square this matrix, you get the 0 matrix. It's called a nilpotent matrix. That's important, as well as the series definition of the matrix exponential.